Today's topic is magnetron sputtering. So, it is one of the deposition process under physical vapor deposition technology, and let us have a quick look to this non-magnetron sputtering, which is commonly known as planar diode sputtering. What are those features and how does it differ from the magnetron sputtering? Now, we can have a sputtering chamber, and here located the target, and this is the substrate. Now, these are the lead wires which is connected to this power supply, and we have a negative polarization, and this can be grounded, and this is actually the substrate. That means receptor surface, receptor of this coating material, which will be dislodged and deducted from this side, and it will come like a flux which will be intercepted by this substrate material. Now, here what we can do further to what we have added, that means this substrate can be also polarized. That means it can also have one negative polarity which is independent of this power supply, and in between we can have a plate which is called the shutter. The whole idea here is to have the best possible clean substrate and clean target. Now, this is one of the very speciality of sputtering process. The whole idea here is to have the virgin surface of the target as well as the clean surface of the substrate, in order that we can have the best possible coating in terms of all the quality, whether it is the mechanical property or electrical property or any functional property. So, that the best effort is made here, and this is here in this sputtering technology we get an edge over any other coating technology, that in situ during the process, once the target material, that means the source material, and the substrate, that means the receptor materials, are admitted inside the chamber, then they are cleaned, and this is done in situ, and that is the speciality of this sputtering process. Now, what we can have, just like the shutter, so here it will be negatively polarized. Similarly, the substrate is also negatively polarized. This is electrical isolation, these are the electrical isolation, and this can be also grounded. So, these are separated, electrically isolated from this chamber, and obviously, here we have a precise metered quantity of argon gas which is admitted. So, rest of the thing, it is according to the principle of sputtering. Now, during this process what happens, this can be grounded with the chamber, and what is going to happen in this case, that sputtering will occur, and that means ejection of the material will take place from this surface. Similarly, dislodgement of the substrate surface, that will also occur. So, in this process, if there be any contaminant, any impurity, oxide scale or anything, any foreign material, that will be removed, and that may be collected on the both sides of the shutter plate, and later that can be cleaned or that can be replaced. And once that is done reasonably, and this is a function of the operational parameter and the time, then what is going to happen, then the shutter is removed, and thereby extending this plasma over this, and then the sputtering starts, and this flux is intercepted by the substrate. So, at the very beginning what happens, at the very beginning the sputtering is done on this top surface and the incoming material is collected from the target. Similarly, it is above the substrate and then it is also collected this material, and then both are now absolutely cleaned and virgin surface. So, here these ions are used, and this is more or less what we can call ion etching, that means removal of the material. So, this one can recognize this very special advantage of sputtering, but this is still what we call DC planar diode sputtering. DC planar sputtering, it is the simplest one, but it is not independent of any difficulty. So, even after realizing that so many flexibility this process can offer, but it has some of the basic weaknesses, and there have been numerous examples of effort to improve the situation and to make the process more efficient, more productive. And that is why what we see, it is now called the non-magnetron sputtering. That means, there will be a magnetron, and that is exactly what we call as magnetron sputtering. Now, what are the limitations of planar diode sputtering? Why one should at all go for this magnetron sputtering? Number one is that to initiate this discharge, what we require a very high voltage, and this is in the order of few kilovolt. It can be reasonably say 3 kilovolt. So, this is 3000 volt that is necessary, and then argon pressure may be 50 millitorr, and which is equivalent to 6.5 Pascal. So, this is also another operational parameter. So, high voltage and high pressure. Now, these are the two things which are at the high end. Now, our requirement is to maximize the cathode current, that means the discharge current. Even with this, the discharge current, even it hardly reaches 1 ampere, and as a result of that, what we get, a ion current density on this target surface hardly, this is 1 ampere the discharge current which can be recorded and measured, and this ion current density, it is hardly, it is in this order, that means 1 milliamp per centimeter square, that is the unit area of this target material. So, even with the best effort, what we can see that this is just the order of ion current density and sputtering rate, that will be maybe around, say this is just an indicative 400 Armstrong per minute. So, that may be one of the indicative value for this. Now, there has been lot of attempt to increase this voltage, but this increase of voltage does not mean that this material erosion rate or sputtering yield will increase, rather it will keep on falling. So, if we consider sputtering yield S, that means atom per ion, it may take a shape something like this even with increase of electron volt. That means, when we increase this discharge voltage, naturally what we try to increase, that means the ion energy. However, at the same time ionization cross section, that will keep on falling, and as a result this sputtering yield will also keep on falling. So, then it is actually the ion energy. So, then it is not a very useful or fruitful method. Another way of doing the thing, that means it is actually this discharge current enhancement augmentation that is done by this argon pressure. However, so there we can see definitely an increase in sputtering yield with increase of pressure, but too much of increase of pressure, what happens, that also restricts the mobility of this sputtered flux of atom from the target, and also easy movement of this ion or the electron, that is also restricted because of the too much of crowding of this argon atom inside, and that is because of this rise of the pressure. So, it is a fact that just by increasing this discharge voltage or this argon pressure, marginal gain may be made, but this cannot be considered as one of the very efficient process. So, what we can summarize here, that if we consider this target and the substrate here, then this is the plasma volume and this is actually the plasma volume, this area, and this is we call cathode dark space. Now, what happens, these secondary electrons, they have a free access and they can move in this direction, and they can impinge on the surface of this receptor surface of this substrate, and in this process it is high energy impingement, thereby increasing the temperature of this substrate, and also it could be that quality of the coating that can be also little bit affected. So, the whole thing is that this secondary electron, it enters this plasma volume and that becomes the primary electron, and then they are going to strike. So, what we see from this whole process, that these secondary electrons are not efficiently used in the close proximity of the target, where we need the concentration of ion and with high energy ion in this vicinity of this target surface. So, that is the whole issue, that how to make this secondary electron which are emitting from this target surface because of the striking of this ions, argon ions here. This not only just cause dislodgement of the target material, but also it is also the emerging of the secondary electron. Now, how to make this secondary electron more efficient? So, that is now the main issue concerning this sputtering process. So, here what we find, that magnetically assisted sputtering, and that is exactly the origin of this magnetron sputtering. In fact, this magnetron, what we mean, it is actually magnetically assisted discharge associated with sputtering. That means, in this sputtering device we have one electric field, and in addition to that there is another magnetic field. So, they are with their combined effect, an attempt is made to make this electron, secondary electron, more efficient, useful. That means, a single electron under the action of both electric and magnetic field will become more efficient. That means, it is expectedly it will generate more number of ions by striking, having more number of collision or hits with the argon neutral once it is coming in the way. So, that is exactly where the magnetic assistance is provided. Now, let us look into this charged particle moving inside one magnetic field. What happens to that? A charged particle is moving inside a uniform magnetic field, and there are two cases. In one, velocity of the charged particle is exactly perpendicular to the direction of magnetic field. Say for example, this is one charged particle having this velocity v, and at the same time we have here one magnetic field, and that is denoted by this symbol B, and if these are at right angle, then perhaps it will be something like that, it will keep on orbiting, and this orbit radius that will be given by. So, here the force will be V into Q into B, where that is the charge, that is the magnetic field, and that is the velocity, and that can be equated by this centrifugal force to which it is subjected, and from there we can get this radius of this spinning radius comes out to be here. This is actually m v by q b. So, this is actually the radius, spinning radius. So, here this angle is 90 degree. So, they are at 90 degree. So, here it will keep on orbiting around this, and this orbiting radius will be r, which is given by m v by q b. Now, this can be, there can be another situation where it is not necessarily they are at right angle. That means, we have this velocity, and then this is the magnetic field, and in between there is one angle theta. So, there will be two component, one will be along B, that means say this is V. So, this will be V cos theta, that means that is along component, and then there will be another component which will be that sine component, which will be at right angle, V sin theta. So, in this case what is going to happen, this is just not spinning, it will be a helical motion. So, helical motion, that means with this V cos theta it will have a drift motion along the magnetic field, but at the same time it will keep on spinning, and as a result we have this helical motion of this charged particle. It may be electron. So, this will be the direction of magnetic field, and that will keep on spinning, and it will be like a spiral motion. So, that will be the motion of the charged particle when it is just not at right angle, but it is making an angle theta with the direction of the magnetic field. So, this is just two examples how this charged particle will behave when it is put in a magnetic field. Now comes, if we now have a electric field in addition to the magnetic field. So, we are coming very close to a situation, very close to a sputtering, where already one electric field it does exist, but what we like to have, we like to add one magnetic field, and this electric field and magnetic field, putting them together with their combined effect, the net result will be to make these electrons more efficient than the case without a magnet. So, that is the thing. Now, presence of electric field in addition to magnetic field, here also we can have two situations. In one case, both fields are parallel to each other. This is one situation, and in this case this electron, this charged particle will have a motion which will be parallel to this field. Both of the field, they are in the same direction. So, the drift motion will be along this field direction, but if they are at right angle to each other, say for example, let us put this way, this is one electric field E, and then we have one magnetic field which is working like this, magnetic field, and so these are the two fields which are very much present, and then how this charge particle will behave. Then there will be a motion called E B drift motion, it is the cross product. So, this is called E V drift motion, and with this drift motion this charge particle will have a velocity with this E B in this direction. So, that will be this E B drift motion, that will be the direction. So, this is very much applicable to this sputtering, where this magnetic force is going to assist the sputtering process or generation of the ion. So, this is actually going to be the drift motion that will assist in generating more number of ions per electron collision, and this is the drift motion. Now, drift motion are at right angle, and exactly what has been shown here, that when they are at right angle. So, with this line, with this mark, we are showing the drift motion, and this is magnetic and that is the electric field. Now, form of the drift motion. Now, form of the drift motion is also very important. It can be, there are two situations, two extremities we would say. One can be a circular motion, that means this drift motion will be very close to that of a circle. So, it will follow almost like a circle. So, it is moving in this direction, but it is also almost following a orbiting, and at the same time it is moving. So, this is a drift motion. So, it is almost following. However, another extremity will be that where we have what we called a cycloidal motion, that means it is something like this. So, it will be more or less like a cycloidal motion. Now, this happens because of the situation, if the energy gained by this charged particle because of the very presence of electric field, if it is larger than the initial energy, then it will be a cycloidal motion. But if it is just the contrary to that, that means the energy gained because of this presence of electric field, that is smaller compared to the initial energy of this charged particle, then that will be more or less like a circular motion. So, one is cycloidal. So, it will move like this. So, it is the drift direction, but it will also have this trajectory. So, this is actually the trajectory, but it is directed in this direction, in this along this line, which is at right angle to this B and E. So, cycloidal and circular. Now, process parameters. Now, one would like to understand and know, and that will be the immediate interest centered around these values: cathode current density, discharge voltage, argon pressure and stand off distance. So, these are the few parameters which will be of immediate interest to any one who will be interested to operate this sputtering device to get a coating having all the required properties. That means, if we have non-magnetron on this side and this is magnetron. So, here cathode current density straightway with a magnetron, a cathode current density of 20 milliampere per square centimeter, it should not be a difficult task to attain, whereas on this side it will be just limited to 1 milliampere per centimeter square of the cathode surface. Discharge voltage, the discharge voltage on this side, it is say an indicative value, not at all exaggerated, it is 3000 volt, but this can be achieved with a voltage say 800 or say between 600 to 800 volt. That is not at all a difficult task. So, on this side one can get just 1 ampere maximum, and on this side 10 to 20 ampere can be very easily achieved. And then the argon pressure, what we have already noted, this is this millitorr, that means it is about 6.5 Pascal, and on this side we can just get down to 1 millitorr, which is equal to 0.13 Pascal. And then standoff distance, that can be quite high. Here it is about 4 centimeter, it can be as high as 20 centimeter. So, if we compare these two, without going into any detail, one can immediately recognize the capability, the efficiency and the productivity of this magnetic field assisted, magnetically enhanced sputtering, and which we call the magnetron sputtering. So, this is the advantage one can very easily recognize with the addition of this magnet in this along with the electric field. Now, current voltage characteristics for a planar diode, that means what we mean here, it is a non-magnetron and a planar diode, it is also DC, but provided with a magnetron. So, we have two sources here, one with a ordinary without having any magnet, and the other one which is backed up, which is having a backup of a magnet. Now, with this, let us have a quick look in this diagram, and this is also another reason how efficient this magnetron is. So, one would be very much interested not only in the magnetron, how good or how efficient the magnet, its geometry, design, its field strength, what should be the best value so far as this current voltage characteristics is concerned. That means, this current voltage characteristics is a true index of the whole process, this discharge, and their magnetron or no magnetron, that picture will be totally clear if we just try to illustrate the whole thing with this graph. So, this is a characteristic feature. On this side we have the discharge voltage, and that is the discharge current, and with this discharge voltage and discharge current, naturally one would be interested to have the line, that means less voltage and more current, that will be the objective of this sputtering or this use of magnet. Now, here we can see two graphs, one may be something like this, this may be one graph. Another graph we can find, this is on this side. Now, here we can just have some, by way of illustration, some indicative value, maybe this is around 3 kV and this is around say 20 ampere and this is just around 1 ampere and this is say few hundreds of volt, 500 volt and this may be around 0.1 ampere. So, from this one would expect that this graph should prevail, and this is the characteristics of Vi, and this is possible only with the use of a magnetron, and this is without a magnetron. We must mention here what was the pressure, argon pressure. Argon pressure in this case, it is of course by way of illustration, this is 6.5 Pa, which gives us 50 millitorr, and this is actually 0.3 Pa, that means 1 millitorr, and this is actually 6 point, this blue line 6.5 Pa Pascal, and that is actually 50 millitorr. So, what we find immediately, the difference between, that means this blue is non-magnetron, this is non-magnetron, and this is with the magnetron. So, the use of the magnetron, that is immediately felt and realized just by looking at these Vi characteristics, and these Vi characteristics we can also put in this form, that this is actually proportional to I, and here we should put, now when it is ohmic conduction, we can put the value of n as 1. However, V is proportional to I in ohmic conduction and this is 1, but however, in this case it is just not 1. So, we should put a value, we should put one index, that is n. So, this n is an index, and that n, that shows the performance of magnetron. So, n is an index showing the performance of the magnetron. So, normally it is our experience that it is varying maybe with from 5 to 9. Now, this value one should look for a higher value. That means, what we get here, this we can put also in this form also, because here it is voltage and current. We can also put in this form I is proportional to V. That means, here it is the voltage which will be applied and to get the cathode current. So, if we can put this way, this is also valid, and this is actually the index here what we can see, and this is actually 5 to 9. That means, from this relationship, what we understand, that to get a level of cathode current, we need certain impressed voltage. Now, what should be its value, whether it will be in the kilo range, a few thousand, or it is in the few hundreds range. So, obviously, our choice, considering all technological constraints and limitation, one would be interested in a low value of V, and that is why to get that same value of current, one has to increase the value of n, and exactly this n means this is the role played by the magnetron. That means, better the quality of the magnetron, more will be the value of, higher will be the value of n, and this n will be showing the performance of the magnetron. Now, planar diode magnetron sputtering source. How it is made? Let us have a look. We can have a planar magnetron, or we can also have a cylindrical magnetron. Now, in this case we can have, say for example, a planar magnetron, a rectangular piece like this, and here what we can have, these are the magnet, these are the magnet with north south poles, and this is a central pole piece. This is the central pole piece which is kept like this. So, that is why this becomes south. So, naturally what we see, this is a rectangular plate and here we have north and this is south. So, lines of force that will flow like this. So, this will be the direction of lines of force, and this way we can have one such configuration. So, this is a rectangular, that means this can be like this. So, this is one rectangular piece, and here we can have, this is actually the cathode or the target material. This is actually the target material, and beneath this we have such a configuration of the magnet, and then we have the electric field in this form. This is the electric field, and then this is the actually the direction of this magnetic field, and as a result of this, with this E B drift, we can have this E B drift motion, and that drift motion, this will be like this. So, drift motion will be in this direction. So, that will be the drift motion. So, here we expect one drift motion, that means these electrons are actually locked. These electrons, secondary electrons, in close proximity of this target, those are locked and those are trapped, and they are forced to orbit following this drift motion. That means, we can expect a drift motion like this. So, this will be the drift motion, that will be the direction. So, the electron will keep on orbiting this path, and that is locked and trapped. However, over this we have to superimpose this cycloidal motion, cycloidal path. So, it will be something like this. So, this will move in this form. So, it will have this motion, and that is directed in this direction, and from this side, when it is on the other side, it will be in this way. So, one thing we observe immediately, that these electrons are actually following this path, at the same time it is also moving along this cycloid, and thereby it is actually following a longer path. It is just not the emission of electron from the cathode and arrival at the anode. So, these electrons are locked, they are trapped in close proximity of the target, and they have such kind of motion, this orbiting and this cycloidal motion. Thereby, the chances of collision with more number of argon neutrals will be more. That means, one electron has now the possibility of splitting more number of argon neutrals into argon ion. Thereby, what is going to happen? We have now a densification of the plasma with a heavy ion flux density, that is the bombardment or impingement over this target surface. So, in this close proximity of this target material, because of this locking of the electrons in this near this surface, we have now concentration of ions which will be generated by this collision as it follows this path, and more number of ions will be generated by one single electron, and there will be densification of the plasma, and that will have a cascading effect. That means, that will lead to larger ion flux, that means ion current density will be more, and finally, it will lead to high sputtering yield, more number of ions per unit time, sputtering yield, erosion rate, and then also the deposition. So, this way one can consider the effectiveness of this magnetron and how it is making the secondary electron more and more efficient, in that it is now capable of splitting and ionizing more number of neutrals than ever before, when it was not trapped or locked by this magnetic field, where it has a free access from moving from this cathode surface to the anode surface, and like that. So, this is one planar target. Instead of this, we can also have cylindrical one. It depends upon the flexibility of a process, or to simplify a process, or to make the sputtering technology rather an easy option for doing the coating. So, in that case, if we have a circular target, then also what we can see, it is going to be a circular target if it is like this. So, here also we have this kind of trajectory. So, this will be exactly the way what we have shown here by this red line, that is the track, that is the drift motion. Here what we are showing by this blue line, that is the drift motion, and over that we have to superimpose by this cycloidal path, and it will go like this over this surface, and it will be just following this longer route, and as a result it becomes more efficient, and chances of ionization of these neutrals will be more. So, this is just one circular plate, but we can also have a cylindrical magnetron. It is a cylindrical, it is almost like a look like a shaft. It looks like a shaft, and it can be placed inside the vacuum chamber, and this is the top side. So, there will be suitable fixture, and this is inside the chamber, and here also we can have the magnetic field. It will be like that, and it can be an electromagnet. So, inside we have this direction of this field, and then this is target, that means that is the cathode. And if we just have the top view of this whole this system, then what we can see, for example, this will be the cylindrical target looking from the top, and then you have the chamber somewhere here, that is the chamber wall. We can have a very quick look, and then this is the wall. So, field will be electrical field will be directed in this way. This is the electrical field, and then this is the magnetic field. So, magnetic field is like this, it is normal to this paper. So, as a result of this, what is going to happen? It is EB drift, and according to this EB drift, there will be a drift motion. So, if this is vertically, now here we have the magnetic field, which is actually upward, vertically upward. So, B is vertically upward, this is the direction of E, and as a result we have at this point E and B. So, that will be the drift motion. So, at each point this will be the drift motion. So, that will be tangential. So, we have a drift motion which is also circular, but over that we have to superimpose this cycloidal motion. So, it will be something like this. Let us put this way. So, this will be the actual path followed by this electron, and it is close to this target or the cathode, and this way it can also shifts the track, and when it is near the wall it will be more circular in nature. That means, here it will be more circular in nature, though it is also following this path, it is also the drift motion. So, this drift motion is like a circular motion, and over that we are actually superimposing a circular form or a cycloidal form. So, this is also another way of sputtering, and in this case the material will be sputtered, and it can be sputtered on in a hollow tube, because it is a cylindrical solid target. So, it can be used for this purpose, for coating this internal surface of a tube. So, this way what we see now, this magnetron, that is actually helping in getting a low discharge voltage, high discharge current, high deposition rate, and the requirement of low pressure. So, with that what we can see, we can also have a look in this what we call this variation of planar diode magnetron sputtering. That means, a normal non-magnetron planar diode system can be converted into a magnetron sputtering system, keeping all the basic feature of this without deviating from the basic feature. That means, it can be a single target magnetron, it can be multi-target magnetron, it can be also a multi-target magnetron with substrate biasing, it can be also magnetron sputtering with a reactive gas. So, it can be reactive magnetron sputtering. So, all the variations are possible just with incorporation of the magnet, and the machine or the apparatus become much more efficient than the case where we do not use the magnet. Now, structure zone model, this is one, we can say this is just like a map. This is just like a map of the structure which is the outcome of any sputtering process. So, let us try to illustrate this point here just by drawing this block diagram. So, this is just like a rectangular block, this is a rectangular block. Thank you. This is just a rectangular block, and in this rectangular block we have few variables of sputtering. For example, along this direction we put this notation T by T m. Now, this T is actually temperature of the substrate, T s by T m, and T m is actually the melting point of the target. T m is the melting point of the target, and this is the temperature of the substrate. And on this side we have the process pressure, and let us put, say, this is 1 millitorr, this is say 10 millitorr, and this is 20 millitorr, and this is 30 millitorr. And here we can now have segmentation of this block to show the structural features of a sputtered coating. That means, a layer is developed by this sputtering process, and let us have a quick look here. Say this is about 0.1. So, this 0.1 means actually 0.1 means T s by T m 0.1, and this is about this zone. So, this is one zone we find, and then we have another zone which comes around at 0.5. So, this is another zone, and this we can also show like that. Then we have another zone around say 0.7, and here it is around 0.8. So, this is 0.5, this is 0.6, and this is 0.8. Okay. So, let us have some discussion on this. So, this one, what is the physical meaning of this diagram? This is actually called Thornton diagram. Thornton diagram, this is actually the mapping. So, here what we see, that if we like to have a structure, and this is called zone 1, this is a transition zone, and this is zone 2, and this is zone 3. Now, zone 1, that is characterized by a porous columnar growth. So, in sputtering it is mostly columnar growth. In the vertical direction it is a growth like a broomstick, and in this side we have a porous structure, and it comes like almost like this. It is a dome, and it is a with a back taper. So, this is a porous structure which is growing, and that is here. So, physically what does it mean? Let us try to understand. If we increase the pressure, then up to 0.5 T s by T m we can expect such a structure which is very, very undesirable. But if we like to have this structure with a small temperature range, which is actually 10% of this cathode melting point, then we have to get down with the process pressure of 1 millitorr. So, from this diagram, one thing we understand immediately, the significance or implication of this low pressure operation. We can have high pressure, and we can ignite the discharge, that means to initiate the sputtering, that can be done with high pressure with much ease, but in that case we will be always left with such a undesirable structure or growth architecture of the coating, and that can prevail even if we increase the substrate temperature even to 50% of that of this cathode material or the target material. But if we like to lower the substrate temperature, which is one of the significant point of sputtering, then if we like to have a deposition with a low temperature, then we must also reduce the process pressure here. So, this way we understand that on one side it is the temperature of the substrate, which should be at the low end considering temperature sensitiveness of the substrate, and at the same time capability of the apparatus to work with a low pressure. Now, here what we have, this is a transition between 1 and 2. Now, what we have in zone 2, these are also sticks, but finer in size and densely packed, and it is also densely packed. So, a transition from this porous to densely packed, that starts within that, and in this case also what we see, if we work at 30 millitorr, it can go up to 0.6 of Ts by Tm, but if we can reduce this pressure, then it can be done with 0.5. So, this is a zone and which will continue up to 0.7 of this ratio with 1 millitorr, but which can be extended with up to 0.8 of Ts by Tm if we increase the pressure. And in the zone 3, what we have, as we increase the temperature, it is actually the diffusion and movement of the mobility of the add atom which are received from the sputtered flux. So, it is actually this mobility of these add atoms and the lateral movement that makes a structure what we call equiaxed. It is very grainy, it is like a grain like structure in that zone 3, and zone 2 broomstick with highly packed broomstick, very dense structure, it is open structure and it is a transition that is changing. So, what we understand from this, that this effect of pressure is extremely important, and if we like to work with a low pressure, then obviously the significance of this magnetron sputtering is immediately felt and immediately understood, and in that case we can work with a low substrate temperature, provided we have the possibility to work with a low pressure, and that is possible by this assistance from this magnet, and that is called magnetically assisted sputtering or magnetron sputtering. So, with this we can summarize the discussion that planar diode sputtering is characterized by the high discharge voltage, high argon pressure, however low discharge current and low deposition rate. These are the limitations. However, the main weakness of simple diode sputtering is inefficient use of secondary electrons. So, these are not properly utilized in this system. When we bring a magnetic field near the target surface, and we have also seen that this magnetic field line is parallel to the target surface, immediately it intensifies the plasma by locking and trapping the electrons, and it is along a trajectory, and that is called the drift motion. So, it has to follow a particularly guided motion, and it cannot be a stray electron, and that will lead to an increase in ion impingement and sputtering rate. So, we also find that magnetron sputtering source reduces the requirement of high voltage, high discharge voltage and high argon pressure, and significantly improves the quality of this sputtered layer or the coating.